Today we're going to cover two things. We're going to cover Atwoods and we're going to cover springs. Atwoods are essentially pulley systems. We'll normally have two masses on a pulley system. Sometimes we'll throw in three on some of the homework questions, but they're not much harder. And you might notice that if they're on a rope, then we're going to be talking about tension a bit more today. We've only covered tension a couple times. We haven't done tons of problems with it. Today we're going to talk a bit more about it. But it's kind of just like an applied force. It's just a force you solve for. And one of the main things to remember while we do these Atwoods is that they're tied. And so if this mass is lighter and this mass is bigger, that means the acceleration is down like it is in the picture. But it means that they have the same acceleration, just opposite directions. So if this accelerates at 5 meters per second squared down, this has got to accelerate at 5 meters per second up, right? Because they're tied together. They're going to move together. And then we also need to remember that tension is the same throughout the rope. We did notes on that the first day. And that's going to be very important for us whenever we solve some of these problems. Tension is the same throughout the rope. There's two ways to tackle Atwoods. We're mainly going to cover the system today. The system is going to be what's going to be able to get us the acceleration. It's going to give us the acceleration. It's going to give us the acceleration the easiest. We can do individual parts and still get acceleration, but it's going to be much harder. Once we find the acceleration, then we can do individual parts, which is it's more algebra intensive, but it's a little bit easier to understand. And then that can be useful to solve for tension. So, because on a problem, I might ask for acceleration, but maybe I'll ask for what's the tension in the rope, in which case you need to be able to do the individual parts and solve for it. And so we'll cover both of those with this example. So the pulley system is set up with two hanging masses, one 15 kilograms, one other is 5 kilograms. What's the acceleration when the masses are set to free fall? And then afterwards, I'm going to ask what is tension, so that way we can cover how to find tension as well. So we'll cover both methods. But let's start with acceleration. I first like to draw a picture. So we have this pulley system here, 15, 5, right? Which means that this is going to accelerate down this way and up this way. So when we solve for a system, instead of thinking about this as like normally do on our axes like this, and figuring out, okay, well, one's moving in the negative y, one's moving in the positive y. What we're going to instead do is think about the system as one long rope. This is just one long rope that is moving at the same time. And so what we can do, and what I like to do, is stretch out the rope. I'm going to draw the 15 mass here and stretch out the rope. Have the 5 mass here, and if you want to, you can draw the pulley in the middle. It doesn't really matter. And we're going to think about what's going on with the system as a whole. Well, if I were to just look at the real drawing, I know that there's not too many forces going on. There's an FG for the 5 block, and there's an FG for the 15 block, and then there's also tension up in both of those. But that's an internal force. Today, we're not going to worry about tension because it's I don't mean today, but in this problem, we're not going to worry about tension because it's internal to the system. It's within the string, okay? We only care about forces that are affecting the system as a whole. Tension is within the string. It's within our blocks. It's within our system. And so this force pulls the system to the right. According to our stretched out version, it's pulling it so that it would want to go that way. While this force, Fg of 15, is pulling it the other way. It's kind of like this tug of war. If we were to stretch this out, force of gravity is pulling it to the right, and force of gravity 15 is pulling it to the left. Don't be scared of these little 5s here. I'm just adding a second subscript just so you know that. The force of gravity for one block is different than the force of gravity for the other block, which should make sense. One block is heavier than the other, so the force of gravities are different. And that's it. There's no other forces here. There's just those two forces, right? Because there's no surface, so there's no normal force. We've already counted for gravity. Our system's a little bit weird. Gravity's not going straight down this time, but that's because we stretched it out, and so we're not really having gravity going left and right. We're just talking about what's affecting the system as a whole. Okay. And so and what's nice about that is because we don't have x and y's, we only need to do one equation. We don't have to do a t-chart, we just need one equation. Sum of the forces equals ma. What we do need to do is we need to establish which way is positive. Well, I always like my acceleration to be positive, and I know this system is going to be going this way. Sorry about that. I know the system is going to be pulled that way, right? Because the left side is heavier. So let's call that my positive direction. Why not, right? It doesn't really matter which way is positive as long as we stay consistent, which means that the other way is negative. And so the sum of the forces, well, that means we have an FG for the 15 block minus the FG for the 5 block. Because of the way we established it, we said left is positive, which means right is negative. And so my left force of gravity is the positive one, while my right force of gravity is to the right, is the negative one. And that's equal to, well, what's the mass of my system? Well, the mass of the system is it's the total mass. Make sure you get the total mass in there. I'm going to write a T for now before we plug in numbers. And then times the acceleration. Okay, so now let's actually plug in numbers. Let's find FG for 15. We have 15 is our mass times 9.8. Since our equation is FG equals mg. Well, what is that? I don't have my calculator on me. Let me type it in real quick. 15 times 9.8. 147. So I have 147 this way. Minus FG5 is equal to 5 times 9.8, which is 49. My total mass is 15 and 5 together, which is 20. And that's equal to my acceleration. And so we just subtract the 2 and then divide by 20. And so 147 minus 149 is 98. And then we divide by 20. And we get acceleration equals 4.9 meter per second squared. Great. We found our acceleration. It's really not too much trouble. We're just subtracting the difference of the two forces. If we want to find tension, though, we realized it was an internal force, right? That's kind of why we didn't talk about it in our force diagram, because it's within the system. If we use a system method, we're only talking about forces that are affecting everything, but tension is only affecting the individual boxes, right? And so, but if we want to find tension, since it's an internal force, we need to dive into the system. And so let's go ahead. All we need to do is pick one of the blocks and isolate it, and then solve it. And so let's pick the 5 block. Why not? It doesn't matter which one you do. So let's pick the 5 mass block. We know there's a force of gravity down, and we know there's tension up. Great. Easy enough. Now I can do my F equals ma for just this one block. I know the sum of the forces is tension minus force of gravity, and it's equal to m times a. My tension is what I'm looking for. I don't know what it is yet. My force of gravity for just that block is 49. Again, if you don't know, Fg equals mg. Our mass is 5. Our g is 9.8, so we just multiply and we get 49. Our mass is just the mass of this block. We're isolating this block because we want the internal force, and so it's just 5 here. But my acceleration is 4.9. This block is moving up at 4.9. If you decided to isolate the other block, you would need a negative 4.9 because that block is moving downwards. Okay, make sure you have the direction in there. That negative or positive is very important. But then now all we have to do is solve for t. So t minus 49 is equal to 5 times 4.9. I don't know what that is. Let me put it in the calculator. 5 times 4.9. 24.5. So T is equal to, well, I'll just add 49. Gives me 73.5. And that's our tension. And if you solve for the other block, you should get the same answer. If we want to real quick, we could do that, but we'll go ahead and move on to save ourselves some time. There is a cheat code here, just like the slopes equation. I gave you guys a little cheat code. I double checked this one. This is the correct equation. So you can copy this down. This will give you the acceleration every time. This will give you the acceleration every time, but again, it doesn't give you the tension force. So that's the problem with this equation. It doesn't give you the tension. And so you would have to do this internal work here, all over here, to find the tension once you have the acceleration. But this will make it easier on you. This only works if you have two masses on a pulley system, okay? So this is M1, this is M2. If you have three masses, like one of the homework problems, it's actually not too much harder though, because what you can basically do is you can just assume, like, instead of saying that this is 5 and this is 7 and this is 3, it's basically the same as just saying that this is 5 and 12, right? These are essentially doing the work of one 12 mass block. And so you can just combine it and then work it as that kind of problem, okay? So it's not that much harder. You just need to think about it. How can I simplify this into a 2 mass system? Even if it does actually is 3 masses, these are doing the work of one mass of 12. So just add them together. If you need extra help with that, come to tutorials and I'll help you with that specific problem. The problem with the other problem with that equation is they're not always perfect. They're not always up and down. Sometimes we have an Atwood over the edge of a cliff. So we have a black mass hanging on a table, off a table, and one's on the table. So how do we do this? We do the same way though. We just work it as a system. So let's stretch out this mass. So we're doing a capital M here and a lowercase m here. And I think this is based off the problem, it's saying that the 10 kilogram one is hanging off the cliff. So that's this one, and then the mass on the surface is 15. Okay. So what force is acting on the system as a whole? Well, I can draw over here. We have force of gravity down. Okay. Tension is internal, so we don't have to worry about tension when we do the system. There is a force of gravity here too, but it's not helping the system at all, right? It's not moving the block to the right, especially because there's also a normal force here, and they're going to cancel out, right? They're balancing each other, so we don't have to worry about that. And so it turns out there's only one force acting on the system. There's just Fg of 10. The other F of G is not moving the block at all. It's just there. And if there's no friction, it's not if there was friction, we might have to add it in there. We're not going to do that in this class. We're not going to worry about it. That's AP stuff. We'll leave friction out of our table questions. So it's just that. So if we were to do the sum of the forces, it's actually not too bad. The only force is Fg of 10. Our mass is the total mass, though, so we need the whole 25. And then we're looking for A. Well, what is Fg of 10? Force of gravity of 10. Fg equals mg, ma. So Fg, if our mass is 10, we're multiplying by 9.8. Oh, it's just 98. That's an easy number to calculate. So we have 98 equals 25 times A. So that means my A it's about 4 something. 9.8, or hold on, 98 divided by, we get, what, 3.92 meters per second squared. Easy enough. If we want to solve for tension in the rope, we can do the same thing, isolate one of the bodies and find the tension. So let's isolate this top body. It doesn't matter which one. Actually, let's actually not do that one. Now that I realize that, it's going to have 3 forces on it, right? If we do the free body, but this one only has 2. So that's going to be easier work. Let's do this one. That one's easier because it only has 2 forces. I like that. I like to make my life easier if I can. So let's isolate the second body. The free body diagram, we have Fg of 10 down, and then we have tension up. And so the sum of the forces is equal to tension minus Fg10 equals Ma. We're looking for tension. We already knew Fg10. We calculated earlier. It was 98. Our mass here is just 10, though, because we're isolating the body. And our acceleration, it's 3.92, but we're moving down, so we need a negative this time. We need to make sure we keep our direction in place. Okay? And so this is the same thing as negative 39.2. We're going to add 98 on both sides. And so you should get a tension is equal to 58.8 newtons. And that's it. Hours aren't too bad. If you have trouble, again, come to tutorials. I have them Tuesdays and Thursdays. They're not horrible if you work them as a system like this, but this does take a little bit of mind bending because we're kind of bending the system the way we think about it. And so there's other ways to approach it as a system, other ways to think about it. If you need help, come to tutorials or look up guides. Again, Atwoods are very popular problems, and so there's other places to find help for them. Springs, we're also going to cover springs today. They're really quick, though. It's just an equation, and we're not going to go deep into them. And so we'll get more into them with energy, but even then, it's not that bad. Force of a spring is just equal to negative kx. K is our spring constant. It just means, bigger K just means a more stiff spring, and it has a unit here. So like mu didn't have a unit, but K does. It's newtons per meter. And then x is just how much it's displaced. So if we have 5 kilogram mass on a table attached to a spring sideways, the spring is compressed that far and it has a spring constant of 160 newton meters. The table has mu of 0.5. What is the acceleration of the mass? Whew, that's a lot. Let's go ahead and organize this data real quick. We have a mass, 5 kilograms. We have a compression for our spring. It's negative 0.25. And it has a spring constant of K is equal to 160 newtons meters. And we do have friction on the table, so we have 0.5. And I want to know the acceleration of the mass. All right, so look at this box. What's going on? So it looks like I have some spring over here, right? And it's being compressed. And so this spring is compressed a little bit, so it's being pushed this way, which means the force is this way. Our compression is to the left, but our force is to the right. Okay? But we're on a surface. Whoops. We're on a surface, and so there's also some sort of frictional force opposing our motion. So let's draw the free body. We have a spring force to the right. Let's go ahead and draw Fg and normal force because these are easy ones. We have a spring force to the right, and then we have friction to the left. And we want to know what's the acceleration. Okay, so let's do our T-chart. Sum of the forces equals ma. Sum of the forces equals ma. This box is not flying off the table and it's not going through the table, and so we're not going to have any acceleration in the y direction. So we really only care about the x side, like normal. Let's start there. We have F of s minus the frictional force is equal to ma. Well, we can calculate F of s, right? F of s is equal to negative kx, which means our F of s is equal to 160 times, or negative 160, I should say, times negative 0.25. And then notice the negative on the x. Then there's a negative there because we're going to the left. The problem did provide the negative, but the problems on the homework I don't think all do. And so you need to decide, all right, are we going to the left or are we going to the right? If we're compressing the spring to the left, that means it's a negative. If we're compressing the spring to the right, it's a positive. It's just your displacement. It's just which way are you going. It's not that compression is always negative and that stretch is always positive. This is not the case. It depends on the actual displacement. Are you moving to the left or are you moving to the right? In this case, we pushed it to the left, and so our force is to the right. But those negatives do cancel out, and so we get, if you multiply all this, you get 40 newtons, which is nice. So we get 40 minus, what's the frictional force? Well, the frictional force is equal to mu times the normal force. So just like normal, we need to go to the y side to find the normal force. Just like it has been, the normal force is just equal to the gravitational force. And if you want to see the work for this, let's do all the steps. Let me go be thorough. Normal force minus Fg equals 0 because the acceleration in the y direction is 0, right? Which means that the normal force is just equal to the gravitational force, which is equal to mg, which is equal to 5 times 9.8, which is equal to 49. So minus 49. It's equal, and that's equal to the mass. 5 times A. And so we get negative 9 equals 5 times A. And so we get A is equal to whatever negative 9 divided by 5 is. So let's do 9 divided by 5, 1.8. And we get our acceleration. Easy enough. It's really not too bad. It's just a different force. It's just another equation. You just got to plug in the stuff, and then you do all the same stuff that we did the first day with the forces. It's not too bad. And I'm not going to do any angles or stuff with spring forces. I'm just going to do a problem probably like this on the test, where it's here's a spring, and here's some friction, and then to find the acceleration. I won't overcomplicate springs because I think the slopes and I think the Atwoods are the most complicated stuff. So I don't want to overcomplicate everything else. With that, I get started on the homework. Let me know if you have any questions. Come to tutorials. Email me any questions, and I'll help you out. Have a good day.